welcome on behalf of Engineering Tomorrow. We are excited to be here to share about aerodynamics and how aircraft are designed. I have a question for all of you. If you could fly anywhere, where would you go? Now, stop and think for a minute. How are you going to get there? Which kind of plane are you going to take? Is it going to be a fast one or a slow one? Does it have a lot of drag or just a little bit of drag? Well, today we're going to talk about all of those different aspects. Before we begin, let me give you a quick background about who I am in my journey as an engineer. As you can see, I was this toddler and I was so curious about how everything worked. I loved those watches that had the clear plastic where you could see the gears turning through them. I loved to take things apart. In fact, I took apart our rotary phone. I unscrewed the sides and then just checked out how all the wiring was all connected. But you guys, the worst thing that I actually took apart was our car door. And I'm sorry to say, I was probably 8 or 9, and my mom actually had to hold the car door shut with her arm and drive us home. It was not a good drive. However, I wanted to take this curiosity and use it for something bigger than myself. And so I had chose to go into the space program. Now, considering where I was from in a small town in Ohio, we didn't have a whole lot of aerospace engineers to talk to about my career path or just questions in general. So I did what anyone would do back in the day, and that was I looked at universities that would maybe help me achieve my dreams. I looked for one, a college that had really good engineering. And then 2, which ones had a whole lot of space people coming from them, how many astronauts had come from them, etc. And so I settled on Purdue University. At Purdue, I studied aeronautical and astronautical engineering, and I did this wonderful thing called a co-op program. Engineering students across the country to be paired with different companies where you get to start working an engineering job right away while you're in school. Raise your hand and let me see. How many of you have ever sat in a classroom and wondered, why is my teacher telling me this? Anyone? Okay, so that was me as well. I remember sitting there thinking, why is my teacher telling me about all the aerodynamic flows underneath the airplane wing and all the calculations? And I know it's important, but how does it all fit together? And that's the beautiful part about the co-op program, where you get to learn a little bit. For one semester, you're in school, and then bam, you go and work an engineering job. You get experience, you make connections in the industry, and you understand how it all fits together. At NASA Langley Research Center, I did some work with the F-18 in the transonic dynamics tunnel, studying how the airflow would go across it. And at the time, the engineering team was looking at how to control buffeting effects. I loved working at NASA, but I still had this big desire to work in the space part of it. So when I graduated, I went down to Johnson Space Center. Now, this is the one down in Texas. This is the one where our astronauts are located and our flight control team. If you've ever heard the phrase, Houston, we have a problem, that's where it comes from. So my job right out of college was to teach the guidance, navigation, and control system for space station. So this meant teaching the astronauts and the flight controllers how the space station would orient with respect to the stars, and how our computer systems would operate what we call our control moment gyros, or our CMGs, and the Russians, and coordinate with them for their thrusters. So I did a lot of work with the Russian computer systems and the different Russian engineers, and I became what they call a Russian training integration instructor. So I got to travel back and forth with our astronauts to help learn about all the different systems for the Russian side of our space station, including how we clean out carbon dioxide out of the air, how we communicate to our satellites up to Houston, or down to Houston, I should say, and also maybe out to our astronauts who are doing spacewalks in all the different systems. When I came back from Russia, I joined the astronaut office as their chief engineer for exploration at the time, which meant I had the opportunity to analyze different vehicles, such as Artemis and the Orion program that would be going to the moon and Mars, as well as laying the foundations for commercial crew program. And you can see in the bottom right-hand corner there that would be our Boeing and our SpaceX vehicles. So that's just me in a nutshell, but we're here for you guys. So I want to hear more about you and help you get ready for your labs today. In Engineering Tomorrow, all of our different labs are created by a team of professional engineers. On the left is Joanne and Edgar. They helped to lead this particular lab for you. And then we also have a team of college students that help to create the content as well. You might be thinking, why would we do this? The important part of having the college students with us is that they can make sure that the content that we're providing for you and all of that is relevant not only to the industry, but also relevant to what you would be learning in your next years when you go to college and beyond. I do have a question for you as we start thinking about the aerodynamic systems. If you had to design a helicopter that would operate on Mars instead of Earth, what things would you have to consider? Go ahead and take a second.
The challenges are many. Ingenuity first must disconnect from the belly of Perseverance. It's a multi-step process already underway. This picture taken Sunday of the detached debris shield. Once Ingenuity is detached, it has 25 hours to gain enough charge from the sun to independently survive a Martian night. Then there's the challenge of actual flight. Mars' atmosphere is only 1% of Earth's atmosphere, so engineers had to develop a special twin rotor system that could provide the necessary lift to get airborne. Also in flight, the helicopter has to control itself, making 500 tiny adjustments every second.
As a lot of you probably guessed, some of the differences that we have between Mars and Earth have to do with the atmosphere. Mars' atmosphere is only 1% of our Earth's atmosphere. And so you can see there, both in our video as well as the picture, there's a twin rotor system that had to be created in order to produce enough lift for Ingenuity, this wonderful helicopter that is now in flights on Mars. Guess what, you guys? I didn't know this, but I researched it recently for you. And that is that it's actually performed 33 flights. So if you've listened to the video, you know that they are talking about it kind of in the future tense. But now, as of September 24th of 2022, it actually had performed 33 different flights on Mars. How incredible is that? Okay, a few other things we needed to think about would be, how we're going to get our energy. We can't just throw up a power line for this particular vehicle. So it has to be able to get some solar energy and charge up its battery so that it's all ready for flight. And lastly, the weather is different when we consider trying to fly on a different planet. So making sure that the different types of heat, radiation, and all of those different conditions will also play into effect. So we've talked just a little bit to give you tips about how Ingenuity was created and how it performs its awesome flights up on Mars. Today, you guys get to be the aeronautical engineers, and you will be doing different aircraft designs and testing them and seeing which ones work. You'll be balancing the forces of an aircraft and then checking out which design is going to work best. Building it, testing it, comparing it, and then contrasting it. Which ones can fly the longest? Is it the same one that can fly the furthest as well? Let's take a look at the different forces that act on an airplane. As a preview, prior to this particular video, you can see there are 4 major forces that we're going to talk about. The lift is the one that's going to take us up into the air. The gravity is pulling the plane down. Drag, pulling us back, and the thrust moving us forward. Take a look at this quick video.
Airplanes stay in the air because of one simple fact. There is no net force on them. And with no net force, an object at rest stays at rest, and an object in motion stays that way, even if it's in midair 10 kilometers above the Earth's surface. Now, of course, it's not like there aren't forces acting on the airplane. Gravity pulls down on the plane itself, plus all of the people and baggage inside, and every single air molecule that's shot through the engines or collides with the fuselage or wings pushes on the plane as well. But if all of these forces are balanced, in particular if the air molecules push the plane up enough to counteract gravity, then the plane stays up. Getting air molecules to push the plane up is the crucial part of flying, and planes do this by making sure the undersides of the wings crash into more air molecules more violently than the upper sides. When a plane is parked on the ground, air molecules bounce off of the top and bottom of the wings in roughly equal amounts, or with equal pressure, and no lift. But in motion, the curved shape of the wings and their slightly inclined angle means that the bottoms smash into more air molecules than before, and smash harder into those molecules, so the pressure on the bottom of the wing goes up. In addition, fewer air molecules now strike the top of the wing, and those that do strike it less forcefully, partly because it's being shielded by its own forward motion, the way running into the rain keeps your back drier, and partly because a curving stream of air has lower pressure on the inside of the curve since the molecules get thrown centripetally to the outside. But whatever the reasons, the pressure on the top of the wing goes down. So low pressure or less downward force on the top, plus high pressure or more upward force on the bottom, and the plane has lift. And if the force imbalance is big enough, it can lift the plane up into the air against gravity. Now, all this crashing into air molecules to lift the plane also pushes to slow the plane down, which it would if not for engines. Engines also push air, in this case backwards, either via a propeller or a jet driving a propeller. For various reasons, it turns out that you want to have a really big propeller driven by a really small jet for the most efficient engine. But even in inefficient engines, the spinning fan blades generate their thrust, which is essentially horizontal lift, by moving quickly through the air with a curved shape and a slightly inclined angle. They're essentially mini wings. And so an airplane is essentially a meta wing. It flies by moving mini wings fast enough to push air molecules backwards, which moves the plane forwards fast enough that its big wings push air molecules down. Whoa. Wingception.
So I hope you enjoyed that awesome video. It does describe how the different forces act on our planes. And you probably noticed that when we take a look at an airplane, not only the shape of the airplane, but also how we have it tilted in the air can make a big difference. So you see that all the different molecules are hitting the bottom surface typically more than the top. And that difference will give us more pressure on the bottom, giving us that upward lift. And that's how we can go up. Let's take a look at each of these in a little more detail. So we have our weight, that is the result of the force of gravity. We have the thrust. Now, you guys, this one used to bother me just a teeny bit when I was in college. We have the engines that are pushing the, explosions, if you will, backward. However, we're showing thrust on the diagram forward. So I'm guessing you all know for every action, there's an equal and opposite what? That's right, reaction. And so that reaction is what's actually taking us forward. So on your diagrams, you'll notice that the arrow forward is definitely our thrust from our engines. And then lastly, our drag and our lift caused by the movement of air. So these two I kind of combine together here, you see, because if we're just sitting on the ground, drag and lift aren't really being a factor for us. But if we're moving through the air, the fact that the air can go across the different parts of our wings is what's going to give us the lift and drag. Taking a closer look at weight and knowing that we have challenged you today to be an aeronautical engineer, what would you do to make your plane fly easier? How can we counteract that weight? Also, if there was a way to reduce the weight of a plane structure, would we need more or less fuel to fly the same distance? What do you think? We can somehow make our structure still very stable and strong, but have less weight. We can definitely go further. So if you take a look at this particular diagram, you can see that the lower weight means less lift is needed to fly. A lot of times you'll see that different companies are now making the materials lighter. They use certain things like aluminum, titanium, or even carbon fiber or composites that will help us decrease the weight of a given plane. Now, you're probably thinking, well, I can make my plane lighter, right? But we also have to make it strong. So there's this trade-off, as in almost every engineering problem. We want lighter materials on one hand, but on the other, we need it to be durable and able to withstand the forces that the plane will be undergoing. So in a lot of instances, you may see that different aircraft companies will actually combine the two. So they'll use a heavier, very strong, durable material for areas that have lots of forces acting on them. But then in the other areas, they can get by with using lighter materials, such as the composites. On the right-hand side, you can see over here, this is the Boeing Dreamliner 787. And this plane is so incredible. I love it because it's actually using 20% less fuel than other planes of its size. But how are they doing it? What they've done is they've taken and redesigned what kind of materials are being used for this particular plane. In fact, 50% of it is fiber reinforced, resin bonded composite materials, you guys. 50%! Isn't that incredible? Half the plane. Also, the piece of the carbon fiber fuselage. So that's like, when we talk about fuselage, that's a term that sometimes you'll hear in aerodynamics a lot. And that's kind of like the body of the plane. So the fuselage itself in this particular plane is one of the largest composite structures ever made that has to be a pressure vessel. And guess what? By using that material, they have reduced 1,200 sheets of aluminum and over 40,000 rivets. Imagine the weight savings of that. So that is how this particular plane is able to work and travel a lot further on less fuel, 20% less fuel. Next, let's take a look at thrust. Again, that's the one going forward, even though our engines are pushing us back. So in your particular design today, you are going to be creating a paper airplane. No, not just like the paper airplanes that you guys are used to seeing and creating when you were smaller. However, we want to challenge you to consider adding details that real airplanes have. In our case, we're going to be looking at the thrust today, and most of our thrust is going to come from our arm movement here of actually releasing the particular airplane. In general, though, when you think of an airplane, you think of thrust as being more continuous along the flight. We don't want our engines to stop. We want it to keep going the whole flight, right? And so we consider that a continuous thrust for a given flight. If you look at an airplane, there is also this component of drag that is acting against the thrust. And that also, you guys, is happening continuously as well. So we have those engines that are continuously firing or giving us propulsion backwards, moving us forward. But because of that forward motion, we have the drag effects as well that we have to counteract. So looking at drag, how many of us in here are either swimmers or runners, maybe football players, anyone that needs to go fast? You may know the effects of drag. So depending on what your uniform is made of, maybe your swimsuit is a special kind. There are even some swimmers that will wear 2 or 3 suits to a practice so that they have lots of drag as they're practicing. And then when they go to the swim meet, they have one suit and it's a lot easier to go a lot faster. When we look at airplanes, though, we want to make sure that as air is flowing over our surfaces, that we've considered this effect of drag as well. So you can see here, there is a very streamlined plane. You can see it almost looks like one of those cartoons of a bee or something. So that is very streamlined, trying to reduce the drag on that particular plane. And then on the right, it's not as streamlined. You can see that as well. So the large flat shapes catches the air and thus it will have more drag. But I got a question for you. Do you think drag is always bad? It's not always bad. For us, if we're trying to get our plane to fly as far as it possibly can, that's not good for us. However, there are times when aeronautical engineers or astronautical engineers might want to use drag to slow a vehicle coming down into the atmosphere. You can imagine the parachute systems of our space vehicles that also, try to increase that drag as we're coming back to slow the vehicle down. Looking at lift. So this is the one that's going to keep us up longer. We have 3 different pictures here on your screen for you. On the left, this is meant to be what we call an airfoil. Now, when I was in college, I remember feeling like I see what it's supposed to be, but in general, it still didn't feel right to me. So let me help explain it a little bit. Imagine that we took this airplane and we actually just cut the wing in half and snapped it off, and then you were looking at it straight on. So that is what that teardrop shape is supposed to be showing for you. Now, from our video, you remember that we have a higher pressure or a higher force on the bottom due to the shape of our given airplane. Typically, you'll want your airplane to have what we call an angle of attack, so that when we have this particular, tilting or that angle of attack, we'll have more of the air molecules hitting that bottom and giving us that lift that we so desire in creating our airplanes. So as there's more airflow going across the bottom and pushing harder up, we have the difference in that pressure for our left-hand picture there. On the opposite end of the spectrum, you can imagine in baseball, someone throwing like a curveball. In our case, for the airplane, we have the lift going up, pushing up. However, with this particular spin on the ball on the right, you can notice that the air is flowing differently. It's flowing kind of the opposite. So there's more ability for the force to be pushing us down with those curveballs. In the middle, though, notice it's totally different. We don't have the difference in the top and the bottom. It's all equal, all symmetric. And so when everything is symmetric like this and there's really no difference in the top or the bottom, you can imagine there's no lift pushing us up or down either. And that's the difference in the left pictures and the right pictures versus the center. As we consider lift, you're probably knowing that different airplanes have different shapes of wings. And we just talked about the fact that if we cut that wing, we can see the difference in air going on the top and the bottom. You also want to take into account how the wing looks. If you want lots of lift, do you think you're going to want a small wing or a big wing? We want more surface where that air can hit the bottom and provide that force of lift for us. As you're creating your particular designs today, I want you to consider though, do you want to have your wings just straight out symmetrical? Do you want to consider having swept back wings? Or do you want your whole body to be a lifting body? Keep these questions in mind as you are going to start designing your own. And you'll have to do 3 different ones. So maybe as you're thinking, maybe you can do 2 different ones, 2 very different looking planes, and see which one is going to work best for you. Now, we've talked about all the forces. You've seen the video. Let's try to put it all together. All right, so taking a look at the plane on the left and the plane on the right, which one do you think is going to fly faster? We can guess that one on the left is going to be faster, and the one on the right is probably going to be slower, but I bet the one on the right can also take more load. And so you can see that although they have different uses, neither plane is better or worse than the other because they're designed for different reasons. One may be designed to go super fast, but the other, on the other hand, may need to be able to carry lots for us. And that's good. Whatever our particular constraints are is what we need to design for. And you guys today have 2 different challenges. One, which one can go further and which one can stay in the air longer. And if you're really lucky, maybe you can get both of those. So in order to talk about our planes, we also have to know how we control them. How do we steer them? You know, it's not going to do us any good if we're trying to go far, but our plane goes off to the left or to the right. So we need to be able to steer. There are 3 major terms that we use in aeronautical engineering or astronautical engineering, and that is roll. Imagine watching Top Gun and they're doing like the barrel rolls. That's what I think of. So you're just going right along the horizontal axis. Roll. Yaw, you're turning left and right. And then pitch. You're going to pitch up. We're probably taking off or something to that effect, right? And then if we're landing, we want to go down. Obviously not too steep because we want to let that come back out. So you pitch, roll, and yaw. All right, so how are we going to do that for our planes? Let's take a look. This diagram is inside your workbook, so I'm not going to read every step by step to you, but I do want to challenge you. Notice that there are like the elevators in the back, the rudder kind of in the middle. I think of it like a boat rudder to help that yaw steering, the leading edge flaps, which can be added, and the winglets out here on the edge of your plane. As you're creating your plane, what kind of wing surface do you want? These are also control surfaces, believe it or not, and the fact that that's where the most of our lift is going to come from. So I'm going to challenge you, at least one of your planes, if not all 3. Try to incorporate some of these different control surfaces and see which one works best for you. Now, let's get right to it. You will see in your workbook 3 different sites, the Fold and Fly, the Iowa State, and the HQ. You are welcome to go to any or all of these. Definitely check them out. Now, knowing that we're going to be testing our airplanes several times, we probably want it to be pretty durable, right? So I am going to choose a plane called the Hunter plane, and I'll show you here why in just a second. Here is one of my Hunter planes, and I'm going to show you how to create it. Notice that the nose is very stiff. There's a lot of stiffness there so that when I fly it, if it hits something, it's not going to get damaged to the point where I can't reuse it, because we are going to test this multiple times and make sure that we're recording all of our information in our workbooks. So we'll do that in just a second. I want to make sure that you know that not only are you creating one, but 3 different types, and your task is to maximize distance, time in the air, or both. Here are just some examples. Again, these are all inside your workbook, so feel free to check those out when you have a second, and let's get started. Hi guys, I am ready to show you how to start making the Hunter plane that we talked about. Again, I really like that plane because of the stiffness. I've tried to use some colored paper because I think it's the easiest way to see how to fold. You're welcome to grab a sheet of paper out and join me in making the Hunter, and it could be one of your 3 if you like. So let's get started. Here we go. Hopefully with the hash marks, you'll be able to see my folding. I am going to fold down about a third of the paper there. Notice that there is this nice fold. However, I'm going to fold it again. So number 2, fold right here. We're looking a little bit like an accordion as I get this. And again, one more time, right down so that it becomes nice and thick. Now here's where the thickness can kind of hurt us a little bit because it starts getting hard to go straight down the center there. Here we go. Now, once you have that fold, we're going to flip it over. And that fold is now going to become the nose of our plane. So we start folding our airplane. Notice that I'm kind of making something similar to like a blended wing body where the entire surface is the lifting structure. You can make yours a little more or a little less, whatever feels natural for you guys. And here is now the nose. Notice how stiff that is. With those 3 folds in there, we've got some good stiffness, which is what we were going for our particular design. Now, in the videos, you'll see how to create that Hunter. You're just going to fold straight down the center line. And again, that thickness can be a blessing and not. There we go. Here, I started altering mine slightly. You'll notice that I added some tape to help hold the sides together. However you see best for yours. I know some people have added just the part of the binder clip here. Whatever works for you. You don't even have to attach it, but it just seemed to work better for me. And then we start bending out our wings. Now again, how much of the surface do you want to be wings? Do you want the whole thing to be the lifting surface? Since we have learned that the lift is coming from the wings themselves, or do you maybe want to add some winglets to it? Let's add some of those. Let's be crazy, right? And we'll add some winglets there for us. Notice though that I do have quite a big lifting surface. My very first one, when I ever made the first one, I only had this much where I really made some pretty tall winglets. So I kind of like it like this. But I'm curious, how are you guys going to make yours? And as you start doing your designs, check out how does that nose look? Does it look pretty good, pretty tight? Is it going to stand up and be durable to many flights? All right, here we go. 3, 2, 1. Oh. All right, guys, how did creating your Hunter planes go? Did they work for you? Are you able to use them multiple times with that stiff nose? I hope so. I'm glad that you stayed till this point. So this is the end of the official first part of your lab. And now we can talk a little further about resources that would be available for you. In your workbook, you'll notice there are 3 different videos available. I really like the first one. It's pretty realistic of what we do in general as aeronautical and astronautical engineers. And in fact, I did several of these things as a co-op. On the right-hand side, this third video has some information about flying cars. It's really neat. However, just know that the voice sounds a little bit robotic. I hope you've enjoyed this particular lab. On behalf of Engineering Tomorrow, I want to thank you for your attention and good luck designing. I can't wait to see what you make. Thanks. Welcome back to Engineering Tomorrow. I am so happy to be here with you, and I'm happy that you stayed to see the extensions we've got planned for you. So we have 4 different extensions with this lab. The first being a launcher, a self-propelled airplane, the relay race you'll see over here on the right, and then in the middle we have the motorized vehicle. So let's go ahead and get started and talk about the details of how you would be creating each one. Looking at the launcher, you'll notice that we have a base. This could be made of anything. The base that I chose to make mine out of was a pizza box. I mean, who doesn't love a reason to eat pizza, right? So it doesn't have to be fancy. Any kind of cardboard will do. I do want to give you a couple tips. So as you look to the right on your screen, you'll notice there's a couple different types of launchers. Of course, I've chosen to create the ones on the right with the cardboard base and using kind of like the slingshot principle where we have the rubber band that helps to provide the additional thrust forward for us, or that launching force. On the left, though, there are also other types that you can create where you actually pull it apart and the airplane shoots forward in that mechanism as well. So if you are choosing to do the one on the right, like I chose, I'm going to give you some tips. First of all, if you remember in the first videos, I had done a Hunter plane. So here is that plane. Now, when I start looking at like how to create my launcher base, the first thing that I noticed was that if I were to just use the cardboard itself, that I would have a problem because there was nowhere for the fuselage, that's the body of the airplane, to go. So I cut out my pizza box to have a hole straight down the middle. This allowed for my plane and the fuselage to fit in there nicely without any interference. You don't have to do that, but for me, when I was doing the launching, that seemed to help. All right, one other tip as you guys get started. So you'll notice on that right, we also have some cardboard pieces that kind of helped to give it a little bit of angle of attack. We want to make sure that we're getting it up into the air and we're not going to just drive it straight across the horizon. So in order to do that, there's a couple ways you could do it. I have created from the side of my pizza box, and I loved using that because if you cut down the flaps that kind of fold down and shut your pizza box, they're all the same size. So that was perfect. I didn't have to worry about the symmetry. I would know that it was going to work. So I cut a slit, kind of like those paper dolls or paper action figures you would see when you were younger. And I cut the slit so that I could just go ahead and stick that part in. Now, guess what? Here's one tip that I noticed. If I did it like that, you'll notice that it kind of rotates and falls flat. So what I did, going back to, our childhood, I cut a slit on this side as well. This one works so much better because it will then fit in both sides and you'll be able to have a nice straight perpendicular part. So those are my tips for this particular one. As you start launching it, I want you to think about how you're going to launch it and how accurate you're going to be. If you remember from the main portion of the lab, you're trying to figure out where your plane gets the best accuracy and the best precision. So in your lab notebook, you will be drawing or pulling over these X's and placing it on the target to show where you landed. Again, we're hoping for the best accuracy hitting the middle of the target, as well as the best precision where it's all happening together. In an ideal world, we're going to be the one on the bottom right. So good luck on this extension. I can't wait to hear how yours goes. All right, here we are at extension number 2. So our self-propelled airplane. As you can see from your kit, you will be getting a propeller to make your airplane. You're probably wondering, how am I going to do this? So if you're thinking back to the main lab, which I hope you are, you're remembering that there's something that's really important for us to get a lot of lift, right? The lift comes from the shape of our airfoil, or in our case, how our plane looks. And so you can see the airfoil here on the screen. It's that shape of the paper on the side of the airplane. So you want to make sure you have a good lifting surface as you do this. So a nice wide airplane wing, and you may even want some additional lift towards the back to help counteract the heaviness of the propeller. It's all about balancing those forces, right? So let's take a look exactly what you're doing. So as I created my particular plane, I'm going to hold it up here. You'll notice that you're going to be connecting your propeller to your rubber band. Now, in the videos that are in your workbook, they do suggest that you put your rubber band through a straw in order to kind of help keep the friction low in case any of that rubber band is maybe touching that wood there. So I just wanted to point that out to you. Mine is not, because I wanted to be able to show you kind of what you're doing. As you rotate your propeller, you're going to like be adding and adding and adding rotation there. We have a couple types of energy. Do you remember the one that's the stored energy? Okay, so we've got a lot of potential energy in this, right? Very good. When we let this go, at the same time, we want to be giving it the force forward. That's going to take our plane forward and get that airflow going over our wing in order to get additional lift. So this is going to be what you're going to be creating. Again, notice all of the kinks in my rubber band as I have rotated it. As I let it go, you'll notice the propeller goes pretty fast. A couple other things that I added to mine. I added some straws across the wings too. If it was just the paper, I felt like it was a little flimsy. And I really wanted some good stability for my plane, both controlling it left and right as well. But also because I didn't want, the wings to be bending down and all of that. So as you're making it, you're going to want to make, 2 layers, one for the upper part of the airfoil or the upper part of the wing, and one for the bottom. I've left mine open so that you could kind of see how I have those stringers and stabilizers going on inside that wing though. So it's going to be exciting. As always, we have in our workbook a video for you to watch in how to create yours. But if you've watched me, you probably already have some tips and ideas of how you'll be creating it. Keep in mind, all of this is balancing forces. So with that additional weight of that propeller, how are you going to balance it? Are you going to add additional mass to the back? Things like that. Keep those in mind. And some tips again about feeding that rubber band through a straw and winding up the plane and throwing it. So good luck with this particular extension. I think you're going to really enjoy it. You stayed for the third one. I'm so glad. So the third one is take whatever airplane you created. Maybe you got the Hunter. Maybe you have the Hunter and the launcher. Maybe you have the propelled plane, or maybe you're going to use all of them. I'm not sure. Whichever one you decided to use, go ahead and form teams in your class. As you do this, you'll notice there's a target. The target that we provide you actually has some scoring, like how good are you? Are you getting the center? If so, you're going to get 7 points. If you're a little further out, you're going to get less points. And the goal here is to have as many points as possible at the end of 2 minutes. So if your teacher is willing to do this, give them a round of applause, because that's a lot of activity going on in their classrooms. But how awesome for you. You're learning so many different things about aerodynamics and how to balance those forces and how to be accurate and precise. So good luck. Notice here, this person has their launcher. These people don't. It's whatever you have designed. I'm curious, whose is going to be the best and most accurate? Good luck, you guys. High five. I'm so glad that you guys stayed for the fourth and final extension. For me, I think we've saved the best for last, because this one here is called the Power Up 2.0, and it will be an electric motor that you get to attach to your airplane. Now, I challenge you. I would love to see you guys actually use whatever airplane that you had from the main lab and use the 2.0 with it. See how it works. You may have to make a few adjustments. So in my case, I could add the Power Up 2.0 directly to my airplane, the Hunter. Now, whoop, it about jumped out of my hand. I would have to make a few adjustments. What adjustments would you recommend? Notice that for my particular Hunter, the propeller's inside the airplane, right? So I probably need to cut off a little bit in order for the propeller to be at the back end. That would be one adjustment that you might make to your airplane. Another one is because the Power Up 2.0, this motor here in the front, is heavy, you might find that as you start to launch your aircraft, let's imagine if something's heavy, what's going to happen to that front part? Yeah, it's going to nosedive. And so you may have to make some adjustments to the back. You'll notice on the screen here that we have a couple elevators to kind of help counteract that and give a little additional balancing for your aircraft. So those are some adjustments that you can do directly to your airplane. But now I want to get into the details of what the Power Up 2.0 is and how you're going to use it. So here is the battery pack. You'll notice here, there is a charge side and a discharge side. The charge side, obviously, we're going to go ahead and connect our motor to the charge side. Notice that it's not moving yet, right? Okay, here we go. And can you hear that? So it has a lot of rotation going on right now, and I'm having to like hold it steady to keep it from jumping out of my hands. So what you will do then is attach this to your plane, go ahead and charge it up, and then when you're ready, release your aircraft. So seeing this motor and then knowing there's going to be a lot of stored energy, we also need the ability to discharge it. So instead of that first set, I'm going to go to that second set. And look at that. It stopped immediately. Let me show you slowly again. Charging. Notice it's going. And discharging. It stops. So those are kind of the things to know about how we're going to charge up our small propeller. Now, the propeller is going to give you some added ability to go further and longer. So I'm going to recommend a couple things for you. Number one, I'm going to recommend that you go into like a high gym area or something to that effect. Number two, I'm going to recommend that you work with your teacher because you only have one of these per class. So each group is going to have a chance to launch their airplane and be able to go retrieve it and then change out the 2.0 onto the next group's plane. So let me show you. There's a couple of areas in your workbook that you'll be able to figure out how to fold these. As you can see on the Power Up 2.0, there are several different types of planes that you are able to create using any kind of folding pattern. And this is just a screenshot of some of the ideas for you. Again, I challenge you, use the plane that you started with first and see what you can do to make it work with the Power Up 2.0. But if you're interested in creating a separate plane that works with the 2.0, you can go to the website and see them there. For now, I'm going to go ahead and show you a quick folding activity in order to get one of these planes ready to go. I'm going to do the Nakamura lock, which you can see here at the bottom. So let's get started. All right, here we go in making our airplane, the Nakamura. So I have some paper. I've put a little bit of designs on both sides so you can kind of help orient you and follow along of how we're going to create this plane. So the first thing we're going to do is fold down the center line. So you should be seeing just the circles on this side right now. Now we're going to fold down the very top, just like we would do a normal paper airplane. At least that's how I think of it. All right, here we have our airplane on both sides. The next thing I'm going to do is open it back up. And I'm going to fold it down like an envelope, okay? So right where that line is, let's fold it straight down. Okay, now you should see our airplane looks like this. I know it doesn't look a whole lot like an airplane quite yet. We're going to take the very top tip and fold it up to the top of our paper here. You'll see why. This is just a marking so that now I'm going to draw a little mark in the center of that particular fold. I'm going to put it in red for you. So here it is in red. And we're going to use that as a guide for where to fold this corner down. So I'm going to take and fold this corner into that red dot. You should be seeing that it starts looking a little bit like a trapezoid. You'll do the next thing with that other side. And so here we have our trapezoid. Almost a trapezoid anyways. All right, so this next part, I'm gonna draw right on the bottom part of our envelope. Notice that what I'm gonna do is I'm gonna lift that up. Guess what? That's gonna lock in those top pieces. So now we have that particular part of the aircraft. And the next thing we're gonna do, you're probably seeing it here, we're gonna fold it down the center line. Notice how that's locked in now. See that? Okay, so with that locked in, we're gonna go ahead and fold down the sides. However you fold it down on this side, remember that the whole goal is to have the most lifting up. And so we want our aircraft to be lifted. So turn it to the next side and be symmetric. Of course, symmetry, as we talked about in the main lab, is super important. So making sure that those line up nicely. Here is our Nakamura plane. So you can kind of see it, how it looks there. The next thing you're going to do is to take your 2.0. Here we go, right? The exciting part. All right, so for our 2.0, I'm going to use, let me see if you can see there. There's these little prongs that go. So those prongs, I'm going to slide into the aircraft right here. Okay. That's it. All right, notice how it wants to kind of rotate already. It's not sitting nicely. So what I'm going to recommend is that you get it inside that fuselage and then we're going to tape it. And so just put a nice piece of tape right across there to hold it all in so it's not going left and right. And once you have that, you are ready for flight. That's exciting stuff. Okay, so now you have your Nakamura. I showed you briefly in the other camera how to attach the motor, but let's just refresh right here. So I'm going to stick it straight down in to my fuselage, and there are those little prongs right at that front there that you're going to slip down the center part of your plane. It should fit in nicely. If you have any trouble, your teacher will be helping aid in this process. You can see it just slides on right just like that. And then again, I would also recommend adding a piece of tape so that your motor shaft is inside the fuselage and not kind of flapping around left or right. So there you go. I cannot wait to see how your motorized aircraft does and how long it stays in the air. Take pictures, take photos. We would love to upload them to our Engineering Tomorrow website. And on behalf of Engineering Tomorrow, thank you so much. I hope you've enjoyed these extensions and I can't wait to see you soon. Thanks.